Next up, we're excited to welcome Aerin Kim. Aerin Kim is the engineering manager at Scale AI, where she leads the conversion of raw data into high-quality training data through machine learning. Prior to Scale, Aerin was a senior research software engineer at Microsoft, where she worked on question answering, semantic parsing, and training data generation for AI applications. Aerin received her master's degree in operations research from the Fu Foundation School of Engineering and Applied Science at Columbia University. Aerin, over to you.
Hi everyone, welcome. My name is Aerin and I'm an engineering manager in quality machine learning team here at Scale. I am very excited to be here to kick off this session, giving you a technical overview of how we use ML at Scale and showing you some of the under the hood components that go into annotation quality management. Quality might sound boring, but if you think about it, quality is precision, recall, and IOU. It is the metric of ML. How tight your bounding box is, how precise your edges are in your segmentation. Did we miss any car, any pedestrian, traffic lights, or important traffic signs in the scene? And when the car is detected, what about its attributes? Can we precisely annotate or predict if the brake light is on or the indicator light is on, etc.? So let's begin. Here's today's agenda. First, I'm going to briefly talk about Scale's recent publication, the data sets that we created and the papers that we wrote. Second, our 3D annotation platform. Third, ML-powered linters that we built to catch incorrect annotations. The first section, Scale's recent publication. We wrote 4 papers this year, 3 were dataset papers, and 1 is a survey paper. The first paper is Fitzpatrick 17K dataset. We labeled 17,000 clinical images following Fitzpatrick's skin type and trained the model on them and evaluated the results with researchers and dermatologists from MIT. Fitzpatrick is a numerical classification schema for human skin color. Type 1 is the lightest in color and most sensitive to sun exposure, and type 6 is the darkest and most sun resistant. So this is an important social service because there is less representation of darker skin in clinical images. And of course, that affects the model prediction. And we wanted to contribute to balancing the data by labeling more darker skins in clinical images. We won the honorable mention award for this work at CVPR Skin Image Analysis Workshop. We also had really good feedback from both computer vision and medical community. The second paper is Reddit 43K dataset. We collected comment and reply pairs from Reddit and annotated those pairs as either agree or disagree or neutral. The data is collected from 5 different forums: Black Lives Matter, Brexit, Climate, Democrats, and Republicans. They are all from hot topics. We evaluated state-of-the-art NLP models on this dataset and investigated what kind of contextual information, for example, graph or temporal, etc., is useful to detect agreement or disagreement. In my opinion, this dataset is very unique and is going to provide interesting research opportunities for people who want to test either text-based method or graph-based method or both combined together. This work is a joint work with Oxford, and we submitted this paper to NeurIPS dataset track this year, the new track, and it's under review. And I think I can share this because dataset track is single blind, unlike its main track. The third paper is natural adversarial object. What is a natural adversarial object? You might have heard of adversarial objects already. Adversarial objects or adversarial examples are the inputs to ML models that we intentionally created to confuse ML models. We usually create those examples by adding small perturbations to the inputs. And adversarial examples are one of the popular research areas in ML robustness and ML security. Natural adversarial object, on the other hand, is called natural because it's an unmodified image. So there's no intentional noise added to the image. So how do we collect these 8,000 naturally occurring adversarial images? We ran the model inference, the efficient DAT, on open images, a dataset of 9 million images, and collected images that broke the model. And broke here means that the image caused the model to make false predictions with high confidence. For example, if you look at this image, the model is very sure that this woman is a bear, and this red Elmo cake is a fire hydrant, and this yellow flower is a banana, and the salmon sushi is a carrot. And when we ran efficient DAT on narrow dataset, natural adversarial object dataset, the mean average precision dropped by 70% compared to when we ran the efficient DAT on MS COCO validation set. So 70% drop is a lot. The model is really helpless on these images. So we investigated why these examples are so confusing to the model. The first experiment that we ran is the integrated gradients. Integrated gradients, TLDR, is an attribution heat map. You literally integrate the gradients of input image, but you don't integrate gradients of just one image, because for you to integrate, you need multiple values. So you start from a black image, all pixel values are 0, and uniformly scale the pixel intensity from 0, the black, to the actual image, and calculate the gradients of all those scaled interpolated images in between, and then add those gradients on top of each other. Then at the end, you average the gradient across all those images, you will see the pixels contributing the most to the predictions. Their integrated gradients will be bigger than the others. So if you look at this image, this fan, the model is pretty sure that this is airplane. So if you look at the integrated gradients, the model doesn't really pay attention to the light in the center, but it paid a lot of attention on blades of the fan and paid very little attention on the background context. So from this, we can see the detection model is relying on mostly pixels within the bounding box and insensitive to the background context. So the second experiment that we ran was shuffling the image patches and running the model again. And the shark on the second image, the model thinks it's an airplane again. And even after image shuffling, the patch shuffling, the model still thinks that it's an airplane. So we learned that the model doesn't use the shape of the object, but rather it relies on the texture or maybe the small subparts of the object. The last paper is our survey paper. We wrote this because we wanted to know what other people have found out about the effectiveness of labeled data in deep learning. We, as engineers working at Scale, the company that powers almost all of the supervised learning in the world, we are huge advocates of supervised learning, but we could be biased, right? So we wanted to survey if there is any way to bypass the supervised learning or labeling itself in downstream tests. And one way to avoid human annotation is to use synthetic labels. You programmatically generate millions of synthetic samples by, for example, using photorealistic assets in multiple different scenes rendered by game engines. That way, you will have full control over data generation, data distribution, and you will have perfect labels. But the limitation is that you will only be able to cover scenarios that you already have. You won't be able to cover the long tail real world edge cases unless you collect the data by yourself and reflect that the distribution during the generation. Another way to reduce the number of annotation is self-supervised learning. By the way, self-supervised learning wasn't a popular term until like 3 years ago. Dr. Yan-Li Kun used to call it predictive unsupervised learning. Predictive unsupervised learning. So it is a rebranded term. It's not something that is brand new. So in retrospect, Globe, BERT, XLM, they all fall into the umbrella of self-supervised learning methods. But when they were published, none of the authors advertised them as self-supervised learning. So for the people who aren't familiar with the term SSL, self-supervised learning, it is a self in a sense that you use your own unlabeled training data for supervision. For example, in language models, you predict the word that comes next, given the sentence, and then compare that prediction with the actual word in corpus. So unless we change the paradigm, like pre-training with SSL, then fine-tuning with the label data, I doubt that we can eliminate the annotation entirely, because intelligence isn't the same thing as autonomy. For example, in NLP, we use pre-trained embeddings such as Globe, BERT, XLM to encode sentences or paragraphs. But for downstream tasks such as question answering, semantic parsing, dialogue system, etc., you would need to define your problem with label data. So the interesting idea for us to pursue now is that not all training samples are created equal. Some could be more informative than others, and ideally we should focus our labeling effort on annotating those more informative samples. And of course, we should keep working on the better formulation of SSL, which could potentially bypass the supervision in downstream tests. The second part of the talk is introducing our 3D annotation platform. Our platform is actually really good, like really well built, and this is how our 3D annotation tools look like. So the data that you see here is PandaSet, the AV LiDAR dataset that Scale created with his high and open sourced. Zoom out, zoom in. In LiDAR data, one frame usually has from 100,000 to 2 million point clouds. And we usually have 60 to 400 frames per task, which covers more than 200 meters of space. So this will be more than 200 meters. And move between frames. You can see the cars moving. Zoom in, zoom out. So it is a massive, complex data. And what I mean by complex is, get out of the bird's eye view, show cuboids, and look at all these taxonomies, right? So road, ground, it's blinking, and the sidewalk, and cars, and medium-sized truck, blinking. A lot of taxonomies. Buildings, rolling containers, other static objects. So there are so many objects here. And on top of that, we are fusing the data from multiple sensors, like camera. So when I mouse over different camera, it shows the angle of the camera view. Move to different frame, and let's click the camera and see. Camera 0. If I click the car, it shows overhead view. Oops. And back view, and dimensions, positions, heading, the yaw or distance. And what's cooler is it's really fused. So if I show cuboids, yeah, if I hover over this car, I can see the back of the car and the back of the truck. And let's look at the camera view one more time. Camera 1, camera 4, camera 2, 5, San Francisco Caltrain station. Back to the lighter view. Then, what else I can show? Let's get out of the top-down view. Trees. Yeah, person. And let's look at the view from the ground. Yes. You can also look at the view from the ground. Eye level. Isn't this amazing? And we can even aggregate all the points throughout the time, the frames. So if I click this, there are massive point clouds because we aggregated all the point clouds throughout the time. And all cuboids, show the cuboids. And bird's eye view. Yeah, you can see the cuboids are moving across the frames. So LiDAR is light detection and ranging. So if you see any non-Tesla self-driving car on the road, you might notice a big spinning cylinder on top of its roof. So that's the LiDAR. And LiDAR is good at identifying objects in long range and determining their speed. And unlike traditional cameras, LiDAR doesn't get blinded coming out of tunnels or in other tough driving conditions such as snow, rain, or darkness. So the tool that you're seeing here isn't, this is not, remove the all tools. This is not just for science experiment. This is an actual production pipeline producing millions of cuboids per week. And this is how we power the entire world's 3D annotation needs. Okay, so that was the introduction of our platform. The last part of the talk is about ML linters that we built at scale. A software engineering linter automatically checks your code for programmatic errors. The ML linter at scale, on the other hand, compares high confidence model predictions with human annotations to surface obviously wrong annotations. Since detecting cars, trucks, or pedestrians isn't old news, I'd like to present something that you don't usually see in research benchmark, which is pole detection using LiDAR. One of the annotation types that our testers tend to miss quite often is pole. And if you look at this image, it's hard to see the pole in distance. So we built a pole detector, and if testers miss the poles, we tell them, hey, you missed a pole. And running this pole linter is a lot more scalable than human reviewing every test manually to trying to find the missing poles. Can you guys see where the pole is missing here in this image? I'll show you later. So this is the outline of the model, point pillar network. This is actually Motional's Alex Lang's work. Actually, he left Motional a few weeks ago, so it's ex-Motional Alex Lang's work. And of course, we modified a lot of details of the network, but the main components are pillar-based. A pillar feature network, 2D backbone, and single-shot detection head. So here's the flow. The raw point cloud data is stacked into pillar tensor. Then the 2D backbone uses those stacked pillars to learn 2D features. Because if you stack the point cloud in a pillar form and look from the above, it's pseudo 2D image. Then the detection head uses backbone encoded 2D features to predict 3D bounding boxes. And as always, the most important question is, where do we get the data? So some of our customers specifically ask us to use their own data to improve their annotation quality. Then we build linter models for them using their data. And we also use our internal synthetic data, augmented data, and sometimes open source data as well. And I'd like to show how much of data science work actually goes into one project if we want to ensure the annotation quality is really high. So once we train the model, what do? We visualize and analyze the model prediction. And one of the thresholds that we need to set for the linter is how sensitive we want our linter to be. Because we do not want the linter to flag a bunch of tasks as false positives, right? And we want to find that optimal balance of precision and recall. So we ran both quantitative and qualitative experiments to set two thresholds. One is the model prediction score, the confidence score, and the other is jitter threshold in XY plane. So the left picture is the 3D visualization of prediction and ground truth. And then the right picture is the bird eye view, the 2D visualization. And as you see, there is slight difference between prediction and ground truth on XY plane. So we plotted multiple curves with different XY threshold from 0.2 meter to 2 meter. And we observed that the curves are fairly stable to jitter within 1 meter range. So we set the jitter threshold as 1 meter. Linter catching missing poles. So this is one example of our qualitative study while setting the threshold. So you see that orange circle, and that is the missing pole. And using the LiDAR data, we are able to see the pole. The pole is above that green cuboid. Another example of linter being useful. The signboard could be seen as a pole from the picture. The pole behind the car is hard to see from the image. Failure mode analysis. There are failures as well if we set the confidence score too low. So sometimes linter thinks of tree trunk as a pole and chimney as a pole. So if you use Scale's annotation service, you'll get all these data science studies as well as an artifact. So that was the LiDAR linter, and we have image linters as well. When the objects are not occluded, we can detect things pretty well with camera data as well. So the white boxes are the cars detected by the linter and not by the testers. Another example is the cars from the other side of the highway were missing, and the linter was able to catch them. So what's good about linter is it not only catches the errors that people make, but also it helps us to build that understanding of those frequent mistakes by people. This is another kind of 2D linter, the SAMSEC linter. We compared testers' work with SAMSEC model's prediction and calculate how different they are. And if the difference, basically cross entropy, is greater than the threshold, we raise an issue. And we catch a lot of spam workers from this SAMSEC linter. So in this specific example, what the linter is flagging here is the testers missed the curve, the pink segmentation. Okay, so this is the end. And thank you so much for watching. I just want to say our ML work is built upon the work of many great engineers and researchers in the community. So the credit goes to them and my team. And I really also want to thank our testers for working with us and discussing things with us and building the best human-in-the-loop system in the world with us. Thank you.